All right, well, I think we've waited long enough and we can get started. Everyone, please welcome Tej from Switzerland, who will be from the University of Bern, in fact, who will be talking about contour deformations in the context of GFMC. Tej, go ahead.
Great. Thanks, Scott, and thanks for the invitation and setting up the seminar and everything. So I'm looking forward to being able to talk about this recent paper, which we got out last month. It's in collaboration with Alessandro Lavato, Noemi Rocco, and Mike Wagman. So not my usual, let's say, co-conspirators on the lattice side. This is a bit of a detour into the land of nuclear Hamiltonian simulations, but it's been quite interesting, and there's some fun knowledge transfer, which seems to have worked well, as I hope to convince you guys. And it's a nice technique that has some bearing on upcoming experiments anywhere where a nuclear target is used and so on. So there's a lot to be gained by trying to study this question of or this technique of Green's function Monte Carlo for nuclear Hamiltonian simulation. And in particular, I'm sure many of the people in the Zoom call are familiar with the method of contour deformation, so that's what I'll be talking about our application of in this context. But just to zoom out for a second and give a bit of framing as to what GFMC is and how it fits into the big picture. So we all know, of course, that there's this rich nuclear landscape of many hundreds of nuclides, which have very particular properties, quite varying as a result of the interplay essentially between a number of different forces. Of course, the strong nuclear force, but also the Coulomb force. The more collective degrees of freedom, Pauli exclusion, et cetera. All of these play a role in determining where exactly a nuclide lands on this chart, whether it's stable or not, what its structure looks like, how it interacts with external currents, and so on. And that richness is in itself, I would say, worth study. But even more particularly, as I'll mention in just a second, I think it's interesting to, and I guess very timely to get as best of a handle as we can on these medium weight nuclei, which appear in many types of experiments as targets, BSM experiments in particular I'm thinking of here, because this is fundamentally important if we ever hope to make a quantitative and constrained discovery of any sort of BSM result. But of course, any of those kind of intermediate mass nuclei are well away from the corner of this plot, which we can actually access in a truly ab initio fashion. So those few baryon number nuclei that we can really access with proper QCD, the theory that really should, at the bottom of it all, describe, well, if we believe QCD is everything, should describe the nuclei, needs to be extended somehow by either these intermediate kind of ab initio techniques or by more model-dependent approaches to these larger nuclei up in the top right corner of this chart. But I'm sort of focused in this middle block in the talk today, and in particular what this kind of what could be termed this microscopic ab initio approach is based on, is setting up the problem of non-relativistic effective nuclear Hamiltonian based on either ab initio inputs, let's say from the lattice, or from data directly from high statistics scattering experiments and so on, that can then be used to predict more intricate details of the properties of these nuclei that we're interested in. And as mentioned, this is quite relevant, especially to just name one example with the upcoming experiment Dune that's going to be taking place in Fermilab and across Fermilab and the Sanford research facility, because this is ultimately one of the biggest determinants of the systematic uncertainty on any sort of measurements that could take place there. If we think about the argon nuclei that will be used as targets, we are interested in asking about cross sections of neutrinos of various flavors with these nuclei. And when we turn to a variety of models to ask what that amplitude is that determines the cross section, we get back results that range over at least several factors, factors of several. And these model uncertainties then really limit the efficiency with which one can pull out any sort of quantitative result from these, let's say, leadership class experiments that generally we're thinking about these days. So any progress that can be made in this direction to, let's say, develop some sort of more principled prediction of these sorts of amplitudes would be quite a beneficial step forward in this realm, which is my particular bias, my particular interest. But of course, there's many other reasons in and of itself to study nuclei, and I think all of this research would be benefited by attempting to solve these problems that appear in these microscopic ab initio methods for nuclear physics. So how exactly do these methods work? Well, the starting point is the nuclear effective Hamiltonian typically. So for example, we might focus on a two-body non-relativistic formulation where we're talking then about a fixed total baryon number, and we're treating our nucleons as point-like particles that behave non-relativistically but have some kind of two-body interaction potential. And that potential can be essentially fitted to the best available data that we have. So for example, one approach, or one leading, I guess, potential in this space is the argon V18 potential. This has been fit to the Nijmegen proton-proton and neutron-proton scattering data, as well as low-energy neutron-neutron scattering data and the deuteron binding energy, and gives a very good fit to these results. Of course, there are known problems with such a potential. It is not, with 100% fidelity going to describe all sorts of nuclear structure and properties, but it provides a good starting point for understanding things like binding energies and response functions to any sort of external probe, for example, interaction with an electron or a neutrino. And of course, these potentials can be improved without changing really the structure of the method I'm about to talk about. So this provides a nice kind of example to keep in mind for what we might apply any sort of Hamiltonian simulation to. Now, just to decompose the structure of this potential a little bit, because this is the actual example that we played with in this case, these two-body interaction terms, they're generally written in terms of these coordinates Rij, which are the displacements between the ith and jth nucleons. And they're written in a factored form. So there's a coordinate space potential as a function of just the distance. And then there are these operators, which also potentially accept the displacement vector because, for example, we allow ourselves to include tensor terms like these Sijs. And so here you have the appearance of these R hats, and this allows you to model spin orbit coupling, for example, in addition to the more primitive operators which you might expect, like the spin-spin coupling and these isospin terms. So of course, sigma here is the Pauli matrices for the spin, and tau is equivalently the Pauli matrices for isospin. Now, this is just 6 of the 18 operators. There's a much more detailed potential that's been written down, and the coefficients and parameters have been fitted to this data. But the details of that are not so important for the story today. And in fact, the numerical studies that we ended up doing focused just on the V16 and V4 prime potentials, which are essentially projections of this V18 onto either the first 6 or the first 4 operators, respectively. So to actually get something useful out of such effective Hamiltonians, one needs some way to find out information about the spectrum of the Hamiltonian, say, or maybe even better, to find out some kind of dynamical information. But let's restrict our ambitions for a second and just say we want to find, for example, the binding energy of some nucleus. So that means we'd like to produce a ground state of the Hamiltonian and understand what its eigenvalue is with respect to that Hamiltonian. So that'll inform us as to what the total energy is and therefore what the binding energy is. So the general idea, the general framework of Green's function Monte Carlo is to use imaginary time evolution to achieve this goal, which maybe sounds familiar to those of you working on lattice field theory. It's a similar framework. There's, again, an imaginary time path integral. Just the formulation of how we go about extracting expectation values is a little bit different, as I'll get to in a moment. But one of those differences is that rather than trying to simulate in general the imaginary time thermal path integral, here in Green's function Monte Carlo, the setup is that one starts with some kind of variational ansatz, so an explicit parameterization of a variationally optimized wave function that hopefully is already close to your ground state, and then applies imaginary time evolution to that, which should hopefully rapidly then bring you to the ground state wave function. Now, to actually implement that, that imaginary time evolution, as usual, we need access to exponentiations of the Hamiltonian matrix. And to do so, as usual, Green's function Monte Carlo relies on these Lee-Trotter-Suzuki decompositions of the exponent of the Hamiltonian. And so, for example, a very standard second order decomposition involves splitting up the potential and the kinetic pieces of the Hamiltonian, which we just saw in the last slide. And this gives an accurate estimate of this short time propagation to order delta t cubed. And so if we evolve this for some macroscopic amount of time, we'll get an approximation to the final imaginary time evolution that's good to order delta t squared. So of course, the key object then is this short time evolution operator. And the name Green's function Monte Carlo is really given to the method by the fact that we're going to work in explicit coordinate space and write down these coordinate space short time propagators or Green's functions, which are the matrix elements of this short time evolution operator, sandwiched between two values of the coordinates on the left and the right. And so these big R's that I'm writing are just the coordinates of the A different nucleons that we're going to be simulating here. So these vectors in principle live in a 3 times A dimensional space. And keeping that in mind, we can then very easily evaluate the application of the exponentiated potential and the application of the exponentiated kinetic operator on these kets. And so doing so, using this Lee-Trotter-Suzuki decomposition gives some kind of matrices that correspond to the exponential, exponentiated potential, and a free kinetic propagator. So this is just the kinetic term exponentiated. And if we flip to the next page, we can see that this decomposition, the free propagator turns into just some kind of Gaussian in coordinate space, which is very easy in principle to treat if that was the only thing. But obviously we have some strong nuclear interactions to worry about. And those are encoded in these S's, which I'm never going to explicitly expand, but they can be easily computed explicitly as matrices in this space of spin isospin vectors. So Green's function Monte Carlo in general is going to be a method in which the coordinates are sampled on each discretized time slice in our imaginary time. But this spin isospin part of the wave function is kept completely explicit. And so, in fact, there's an exponentially large vector that we could call the wave function, evaluated at some coordinate r. The dimensionality here is just set by, if we truncate it by assuming we fix the total z component of isospin. Naively, you might think 4 to the a for the 4-dimensional spin isospin space and a different nucleons. But in either approach, it's exponentially large, but for small enough a, this is something that one could still represent. And so you can carry around these essentially these wave functions evaluated at particular coordinates. You can evolve them according to the potential terms, which are now these matrices, which are exponentially large in A, but still tractable for reasonable A's that we might consider. And you can evolve the coordinates then according to this free propagator, so some kind of diffusion process, as we'll get to in just a second.
Before you go on, could I ask?
Yeah.
Is the advantage, I mean, everyone for these problems uses GFMC rather than something like a thermal path integral. Is the advantage to GFMC over a thermal path integral just that you get to start with a good ansatz, and so you need less Euclidean time evolution, or is there some other important advantage?
I think, as I understand it, I think that's the main advantage. But the other one being that GFMC, if we actually look at the method, which I'll decompose this slide in just a second, but there's a series of steps where you essentially are recursively generating the next coordinates by this kind of diffusion process. And this doesn't fit naturally with having some kind of periodic imaginary time direction, because then your recursion would be circular. So of course, you could then try to do GFMC in maybe the thermal path integral GFMC, but it would be looking a little bit more like having to do a lattice field theory calculation, where then you need some kind of Markov chain to thermalize, and you build an ensemble that way. Whereas in GFMC, there's no Markov chain. You just sample directly because you've opened up the boundary, the imaginary time boundaries. And since you hopefully have a good variational ansatz to begin with, this is sort of fine.
Gotcha. Thanks.
No problem. Okay, so let me say a little bit about that recursive sampling, because that is a key feature of GFMC. It doesn't inform too much the actual approach to the sign problem we take, but it is useful to keep in mind because it maybe slightly modifies the way we set up the problem in the first place. So we have in principle a path integral definition where we insert a bunch of these Green's functions. So here I've collected together the potential parts of the short time evolution and the free terms, but this is in principle just n different steps of evolving by time delta t up to, again, that trotterization error. And one could try to do some kind of Markov chain simulation of this by sampling all of the coordinates on all time steps and updating them stochastically to converge to the right path integral distribution. But the fact that we have a variational ansatz to begin with allows one to just do a direct sampling of this path integral, or at least a reasonably good approximation to directly sampling this path integral. So the approach is to sample, well, to start with the 0th time step, to sample from this trial wave function. And this might require some kind of Markov chain, metropolis sampling, something like that, but it's a much easier problem because there's no time direction. And so you just have the coordinates of the particles to sample from your variational wave function. And typically also these variational wave functions are simply parameterized such that this would be possible. And then the idea is to sample successive coordinates. So starting from R0, we should then sample R1, which is one step of delta tau forward in imaginary time, and then R2, R3, and so on. And to do so, ideally, one would draw the nth set of coordinates of the A nucleons conditioned on all the previous coordinates that have been seen in the path. And so one way to do this sampling would be to define this important sampling weight, where here we're now sandwiching on the left side also the trial wave function so that it becomes easy to compute expectation values like the one shown below here, where you ask about imaginary time sandwiched between two copies of the trial wave function. And so if you could sample directly from this weight, this is some conditional distribution. In principle, you might have a way to sample it. Then you could pull out the coordinates for the next step, and then condition on that again, you could sample the coordinates for the next step, and so on. And so in one shot, you get your sampling of your full ensemble, or you get maybe a single sample, and then you can run this repeatedly to draw an ensemble and compute then some expectation values of any observable you might be interested in. Now, it's typically not possible to exactly sample this important sampling weight. So the typical approach is to apply diffusion according to this kinetic operator, which is a Gaussian, is actually easily sampleable, and then do some kind of either population resampling techniques or heat path over different proposals to somehow incorporate this term in square brackets, which is the other part of the important sampling weight that hopefully guides in a more physically meaningful way the evolution of your coordinates. Because of course the diffusion term alone clearly is not going to show you anything interesting, or will not tell you anything interesting about say the binding of nuclei or anything like that, or any interaction. It's just a free theory if we only simulate according to this. But okay, so one can apply these techniques, get some sort of ensemble that samples this path integral, and compute observables. So seems like all is well and good, but there is unfortunately problems afflicting this approach, much like every other method you might cook up. And in this case, one of the main problems in GFMC is the so-called fermionic sign problem. So this important sampling weight, I've lied a little bit. I asked you to sample from it, but it may or may not actually be positive. So it may not make sense to even sample from this. Now, of course, that means if this is not going to be positive definite, then it doesn't define a probability distribution. But maybe a natural way to go about this would be that you sample according to just the absolute value of I, and you reweight in the phase factors. And you should do this in the numerator of your observable and in the denominator, which provides the normalization as well. So that's fine unless you have some kind of exponentially bad sign problem in that reweighting factor. And unfortunately, typically this would be the case. So for example, this S, which is the collection of all of those exponentiated terms coming from the potential, will include things like the exponentials of the tensor operators, which we saw a few slides ago in this AV18 potential. And those give non-trivial phases. So in general, this is going to pick up some kind of sign or phase fluctuations. And at large imaginary time, as you can see just in this random example here, for example, lithium-6, at large imaginary times tau, the error grows. And of course, this limits the precision with which you're able to extract physics that you're interested in, such as the binding energy. So ideally, we'd like some way to approach this problem. And here's where I take inspiration from things that I'm more familiar with, such namely contour deformations in the context of lattice field theories. So this has been applied by several of the people also in this call to some lattice field theories of complex actions to great success. And there's continuing efforts, of course, to continue to apply this to more and more theories. So the question is, can we draw inspiration from these approaches in this other context and apply this in the case of GFMC, which seems to be a nice way to access some intermediate scale nuclei and predict some properties that will be relevant for our studies of interest in the future. So it's a different path integral because it's this non-relativistic coordinate space nuclear path integral. It's not a field theory, and so there's no integral over field degrees of freedom, but it's a similar structure. It's just, if we want to think about contour deformation of this, we just think of it as a 3a times n dimensional integral. And so again, that's just some high dimensional integral that we can hope to deform the contour of integration of and make some progress. So this is just transcribing the path integral that we wrote down 2 slides ago. And the point is, this is, if we look at the measure, this is just integration over r to the 3a times n. So there's 3a degrees of freedom per time slice and n time slices. And altogether, we're integrating over all of these simultaneously. And so if this integrand is holomorphic, we are free in principle to deform this into a submanifold of c to the 3a times n, which in general I'll write with tildes when we do these deformations. And we can then just plug in our deformed coordinates. Maybe we have to expand this deformed measure also and appropriately account for a Jacobian. But having done so, then Cauchy's theorem would guarantee us that we're not introducing any bias. We're still computing the same GFMC expectation values. And maybe if we chose a good contour, we would be making progress. So let me talk about this sort of thorny point of the demand for a holomorphic integrand. So in the lattice field theory case, it's generally almost immediate that the path integrand is holomorphic. But this may or may not be true. On the face of it, it's not true of Green's function Monte Carlo path integrals, because these potential terms are written in terms of the magnitude of the displacement vectors Rij between the nucleons. And so that absolute value looks a little suspicious, looks a little worrying for analyticity, complex analyticity, of course. But in practice, these are just some functions that we wrote down that depend on the displacement vectors, but just came from data. And so we are in principle free to rewrite their functional form in a way that matches the data or really agrees with the original function on the domain of interest. So namely on the real line and for ranges of displacements that are typical in the physical problem. And otherwise we can choose our parameterization sort of freely. And so, for example, in our case, we worked with a Chebyshev parameterization, which is provides an excellent approximation to these potential functions on a fixed interval of the real line. And is fundamentally just a polynomial and is therefore holomorphic as long as we feed it as input, not the magnitude of Rij, but the magnitude squared. So Rij dot Rij. And it's important that I write it this way and not as magnitude squared, because this implicitly defines the analytic continuation then of this function to complex coordinates Rij. But having done so, as you can see from the plots here, we still have a good approximation to the potentials up to some endpoint effects, which could easily be fixed by going to a slightly higher order. But for the sake of a preliminary study, we've essentially just gotten an approximation that has a good chi-squared to begin with. And taking this, then we're free to now evaluate this on deformed coordinates with no worries about holomorphy problems. Now, that just needs to be done to everything else in the GFMC path integral. So the trial wave function, we can do the same thing. Typically, again, that's parameterized with some sort of function of the displacement, of the distance, sorry. So the absolute value of these displacement vectors. But it's just as easy to come up with some parameterization in terms of the R squared coordinates, these rows, and that can be fit to the actual data, or in this case, really the variational wave function that we started with in physically relevant ranges of distances. And finally, we should make sure that our momentum operator, which is the only other thing aside from these coordinate operators that appears in our path integral, we should make sure that that works out okay. But that's straightforward enough. This turns into some sort of derivatives with respect to the coordinates. And in general, we can just exactly evaluate these derivatives on and propagate them into the path integral. And what we're left with is a path integrand that is truly holomorphic and can be, in principle, deformed into the complex plane, or the plane of complex coordinates. So this sets us up. Yeah, go ahead.
Do you have an idea for how sensitive this method is going to be to your choice of holomorphic fit function, right? So here you chose Chebyshev. If I fit it in some other way, then it'll be a very good fit on the real axis again, but it could differ substantially elsewhere. Do you have an idea of how much that matters? For instance, how far are your contours going to be deformed in the complex plane?
Yeah, so this would be something I think that would be interesting to study numerically, which we haven't done. But I think on an intuitive level, the idea is that the analytic continuation is determined well close to the real line by the shape of the function on the real line. Of course, there's sort of a caveat here, because you can always imagine some kind of, let's say, high frequency, small amplitude deviation away from what your actual function is. And if you think about, let's say, a high frequency exponential oscillation, that turns into a large amplitude exponential in the complex plane. And so really I would say the main source of uncertainties close to the real line are uncertainties in these small amplitude, high frequency terms. But on sort of physical grounds, we don't expect such high frequency terms to really exist in these, either the potentials or the wave functions. So I think it's somehow probably quite reasonable, both physically and then practically speaking, to just have these fits to some reasonable low, let's say smooth or low frequency functions. Then beyond that, what actual function you take could affect the practical performance. But because these should all agree in that region close to the real line, which is where you ideally have probably a reasonable initial noise improvement of the problem, I would sort of think that as long as we're doing something sensible, so not including any of these really high frequency modes or high orders in our polynomial, then I wouldn't expect this to be having a significant effect. And of course, the point is, any such choice we make has to agree with the integral of the fitting function on the real line. And so if the integral of the fitting function on the real line is very, very close to the true function on the real line, then your final integrated number can only be affected by a very small amount. So it's going to agree very well if you are solving the sign problem. Yeah, this is just to say, again, it's a question of practical efficiency. And I think we would be interested in the next steps of trying some other parameterizations, but Chebyshev so far is giving very stable results, even to the order that we're using it at, which is n equals 150. So maybe that gives some intuition, but the rest is up to probably future study. So hopefully that answers your question.
Yeah, thanks.
Great. Then, all right, so we've set ourselves up to be able to do deformations. We've solved the question of writing the path integral in a holomorphic form. We know what path integral we're trying to evaluate in the first place. So the remaining question is just how to do the deformation and how to optimize that deformation. So an obvious choice that comes to mind is just stay in the Cartesian coordinate system and try some simple parameterizations in terms of Cartesian coordinates. The very obvious one then is just to have a constant shift into the imaginary direction of each component of every coordinate everywhere in the path integral. And so since this is a constant shift, there's no Jacobian factor, and the number of parameters is easily counted. It's just the same as the dimensionality of the original path integral. So one parameter per coordinate. And it's very simple, but as we'll see momentarily, this actually already gives pretty good benefits in the case of the Euclidean density response functions. Of course, if we're running up against a wall, or if we're trying to see if some better results can be achieved, it would be interesting to look at additional coordinate dependence. So maybe making these imaginary shifts functions of all coordinates. In doing so, of course, it's important that we are still able to compute the Jacobian factor. So either some kind of manifestly triangular Jacobian would be necessary to use here, or some approach where the Jacobian could be straightforwardly numerically integrated. For example, if we're defining our deformation according to something like the holomorphic gradient flow, although we've tried neither of these in this case, given the good success of the simple choice so far. On the other hand, we could also choose to turn to a spherical coordinate system and do the same procedure. Now, of course, if we really write down a totally general deformation, then it should not matter whether we started with the Cartesian coordinates or the spherical coordinates. But since we're restricting to these kind of simplified families, it made sense for us. And as we'll see momentarily, it was actually inspired by the structure of our observable to work with these spherical coordinates and to think about deforming, again, by a constant shift, just the polar angle. So this is the one that is 2 pi periodic out of the 3 coordinates in spherical coordinates. And since this is just a shift, it again has no Jacobian factor. Now there's just one for every choice of nucleon and time step. So it's only a times n free parameters. So again, this is a fairly small or limited parameterization. But it does already make progress in the case of the binding energy. So this one turns out to be useful for the binding energy. The previous one turns out to be useful for the Euclidean density response. Again, we could be a bit more general. I'm not deforming r and theta here yet, but we could imagine trying to write something down. To do so, we have to be a little bit careful about the endpoints because the domain of integration has boundary for theta and r. In the case of theta, it's typically defined from 0 to pi, and so those 2 points had better remain fixed. And for r, it's from 0 to infinity. I glossed over this in the previous slide. We should potentially worry a little about the behavior at infinity, but certainly we should also worry about the behavior at 0 if we're working in this coordinate system. And if we do more general deformations that don't just look like a constant, also for phi, it's important to treat the periodicity in the real direction. And so we can actually kind of picture the domain of complexified phi as looking like some kind of cylinder. The real direction is a circle, the imaginary direction is this line. And the constant shifts we're doing just look like moving that circle up and down, but we could do something more, say, wavy or complicated as long as it keeps that winding number around the cylinder. So these 2 types of deformations we'll explore, and we looked at this in the context of the deuteron as the simplest non-trivial nuclear system that could be treated. I should mention, yes, also to actually optimize these parameters, it's important to have some kind of numerical approach because it's not obvious a priori what a useful choice of parameters would be analytically. And so we take the standard approach in this study, and we just write down a loss function that captures something about the variance of observables that we're interested in, and then optimize that numerically using stochastic gradient descent. Now, this is maybe a little different than what's sometimes done in the complex action lattice field theory case. So here we really did find it useful to optimize this loss function as a function of the observable, and also include that numerator involving the observable in the loss. So you can see there's two terms here. One of these is the log variance of the denominator, which is independent of the observable. And one of these is the log variance of the numerator, which does depend on the observable. And so we, in principle, would have to run this optimization for every choice of observable. Of course, there are tricks that one can do, like transfer learning. So taking the optimized set of parameters for one observable and using it to initialize the optimization for a related observable. And this we did take advantage of, and it does significantly speed up the optimization. So it's not as bad as having to do, let's say, a full run of stochastic gradient descent for each choice of observable, but we do need to do a bit more work than just finding a sort of global theory-dependent choice of deformation. So, okay, this sets up some kind of loss function, and it's really just some particular parameterization of the log variance. Here we had, for example, a tunable hyperparameter to choose between how much we want to emphasize removing the sign problem in the numerator versus the denominator. And we simply tried a conservative choice of 1/2. So just trying to solve the sign problem simultaneously and equally in both the numerator and denominator. And this, at least in the case of the Euclidean density response, where we have significant progress, seems to be plenty enough to guide the optimization to a useful point. Okay, so now I can actually come to the deuteron, which is our kind of case study of all of these approaches. So there's two observables that we considered. One is the simple binding energy. And this, as I have sort of talked about in generality in the previous few slides, is just a matter of taking our variational wave function, evolving it in imaginary time, and then measuring the expectation value of the Hamiltonian, which should give us a good approximation to that ground state energy. But it's actually, this problem is too easy somehow, because if we, even working with the AV6 potential, if we optimize a variational wave function to start with that's tuned for the AV6 potential, you basically are already converged to the right binding energy. And after a few time steps, you really get a very accurate result. And so there's no regime where you would be interested in going to the large imaginary time evolution. So we cooked up a sign problem, which is more analogous to what you see in these larger nuclei, for example, that lithium plot I showed towards the beginning. And to do so, we just set up a variational wave function that was bad. We optimized the variational wave function for the AV4 potential, and then evolved it according to the more complicated AV6 potential. And because the structures are quite different, and AV6 includes this tensor operator that AV4 does not, there then was a very poor overlap onto the ground state, and long imaginary time was required to actually converge. And there you do see growing errors. So the potential looks like just some very trivial spin isospin wave function, because AV4 has this very simple structure, times some coordinate dependent simple weight factor. And because this is an eigenstate of the spin isospin operators, there's really no issue with the potential, the AV4 terms of the potential. But the tensor operator, we can expand and actually see kind of very explicitly where a sign problem is coming from in the setup. So just taking the spin orbit coupling part of the tensor operator and expanding this out in pure matrix form. So we're looking at now a spin-spin matrix for the first and the second particle here. We can see that there are these spin flip terms that flip from up to down or down to up. And that's where the phase comes in. Okay, also there's a sign problem, maybe from this minus sign in the down to down. But mainly the point is we start with the two nucleons and spin up. And as we flip it to spin down, we pick up some phase that's coordinate dependent. And as it flips back and forth from spin up and down, we keep picking up these phases. And of course, that's necessary to capture the physics. But in the long run, this produces some kind of sign problem. And this inspires a deformation, especially when we look at this structure where the phase has to do with e to the I phi, where phi is in spherical coordinates that polar angle. This inspires a deformation analogous to the one we talked about before. So just taking that phi angle and shifting it by a constant amount in the imaginary direction. And it's a simple exercise to plug that into this term in the potential. And it turns out that the effect is just to suppress the magnitude of the first spin components and to enhance the magnitude of the second spin component. So to suppress the up spin components and to enhance the down spin components. And so the idea is that if we suppress in this way the spin flip from up to down, and we pick up these exponentially small factors, or rather factors that are less than 1 every time we make a time step, then on average, hopefully the magnitude sample by sample will be exponentially smaller than it would be in the usual GFMC. And so the phase, therefore, because we don't compromise correctness, would have to be that much more coherent to still achieve the same expectation value. This is just looking at one time step, but the same story sort of applies for multiple time steps. You just need to have this kind of ramp structure where the lambda value increases as I go step by step, so that you actually do pick up a suppression of the magnitude asymptotically in tau. So this was sort of the analytic reason to choose spherical coordinates, the intuitive reason, and this is our intuitive guess for a useful deformation based on this, some kind of ramp structure. And then we threw this into the actual GFMC evolution optimization loop and tried this with a generic lambda of tau, so still with constant shift per angle. But this choice of shift could be different at for each different nucleon and each different time step as well. And the result is actually quite similar to the ramp contour. So out of this ramp structure, of course, we're free to set the magnitude as we will. The previous analysis didn't really prescribe the magnitude of the ramp, but simple kind of hand tuning to improve the variance as much as possible give a magnitude of order 0.25 for this ramp. And the trained contour, which had no knowledge of the ramp or anything, seems to converge to something quite similar. So this is informing us that our ansatz, at least, was based on some reasonable intuition, and the training then confirms that a ramp-like structure is really a decent way in this parametrization to make progress on the sign problem. Now, the result is not amazing, so maybe let me draw your attention first to the left. We compare here the expectation of the Hamiltonian, so our estimate of the binding energy as we evolve in imaginary time. You can see here this really is showing the poor overlap of the trial wave function onto the ground state, because it takes a long time to converge, even in the original approach. And we can see then that this is reproduced accurately by the deformed contours, as it should be, because Cauchy's theorem guarantees us that the expectation value will not be changed. But if we look on the right side, there is some improvement in the errors. The factor is just not as large as sort of exponential gains that have been seen in certain other cases. But one can see that over the range of evolution used here to converge to around the ground state, this factor of the error of the original contour versus the deformed contour, which is basically a measure of the improvement in the error, maybe is consistent with a 20–30% improvement at large tau, but no spectacular changes maybe in the binding energy. So then we also considered a second observable, this Euclidean response that I was talking about. And here, because the observable itself has a strong sign problem, there was no need to do this trick of making a bad variational wave function. So we just start with a useful wave function optimized actually for AV6 and evolved also with the AV6 potential, and then study this Euclidean response observable. So generically for two currents J prime and J, we can look at this function where essentially I take my initial state and I kick it with some momentum Q and some operator, then evolve for imaginary time tau, and then I unkick it, or I kick the bra, you could say, on the left side with a different current, or possibly the same current. And of some interest as a candidate observable in this class is the density response function in particular. So if I make those currents be the number operators for the ith particles projected to some momentum q, then I can plug this into my formulation and I have some kind of Euclidean density responses rho sub ij, where these are the nucleon indices. And one can see just immediately from the form of this that there is what looks to be an oscillating phase factor here, the e to the iq dot the coordinate at the last time step n minus the coordinate at the initial time step 0. So this visually seems to give some kind of sign problem, but we can actually check it against some actual analytic results here. So looking at the full Euclidean density response, which would be summing over these nucleon coordinates, since we're just imagining hitting the nucleus as a whole with some current and not specifying which nucleon it actually targets, then this, since we haven't subtracted off the full elastic contribution, it gives some kind of, it should have some expectation value that scales like e to the minus tau q squared over 4 mn. So this is simply the non-relativistic energy associated with having elastically scattered our full nucleus, which in this case is a deuteron with mass 2 mn. So this falls off exponentially in tau. Meanwhile, the average magnitudes of the sample by sample estimates of rho are order 1 because it's just this e to the I q dot r factor. And so this is an exponentially severe sign problem in principle. At large tau, we would need exponentially severe phase cancellation to get this small expectation value out of samples that have order 1 magnitudes. But also the structure of that exponential factor suggested a deformation in this case as well, in particular the Cartesian coordinates deformation. So if we're looking, again, I'm focusing on the deuterons, there's only two nucleon coordinates to worry about. And if we work in the center of mass frame, we're forced to have an opposite deformation for R1 and R2. But these deformations could in principle be arbitrary or it could be a function of Q and it could be arbitrary across tau. So we can ask what deformation makes sense here to reproduce this kind of exponential scaling in the magnitude itself to avoid needing some phase cancellation to reproduce that expectation value. And the sort of simple pen and paper calculation shows that if I fix the two endpoints of the shift into the imaginary direction according to this function that somehow depends on the momentum q and also depends on this typical magnitude of the expectation value, then you deform your observable part of the path integral exactly in the way you would want. So it already pulls out this exponential dependence. And as long as you don't pick up too much noise from the rest of the path integral, you've clearly made a lot of progress here. So we tried out some deformations in this way, both with these, again, hand-selected ramp parameterization, so to speak, ones that just interpolate between these endpoint conditions that analytically are inspired versus a numerical optimization of the Cartesian coordinate shifts. And maybe surprisingly, but yeah, sorry. So if we compare these one-to-one, you might be a little surprised to see that the ramp is actually lining up quite well with the trained contours, especially in these cross terms where you have your two currents acting on the two different nucleons in the deuteron. But the point is we took these ramps as inspiration essentially from the trained results here. So in this case, the ramp was just inspired by this simple analytic argument, but you can see this shape is very particularly just designed to match the symmetric nature of the off-diagonal terms of the Euclidean response. So this is a case where the training kind of gave inspiration for a very simple then one parameter family. And if you look at the results, we end up comparing just the ramp results because the trained results are essentially equivalent in terms of the improvements that we see. But if we take a look at these plots, these are just now for different momenta of the Euclidean response. We can compare in all cases the original Euclidean response at various imaginary times versus our optimized ramp deformation. And shown just for comparison, because sometimes the original is quite noisy, we also have an original with 10 times the statistics of either of these two evaluations as sort of a ground truth. These are also all rescaled against that elastic factor. So if it was if the Euclidean response was purely the elastic response, this would be a flat line, but any deviation shows you some kind of substructure of the interaction of this current with the nucleus. And we see, in fact, that there is just visually reduction in terms of the magnitude of the errors when we go to the deformed result versus the original result. And in some cases where you might not have really even been able to see the asymptotic behavior from the original results, you are able to see it with the deformed results, and it confirms what you get by multiplying your statistics by 10. Now, we can also just try and get a handle on how much improvement we're actually getting and how it scales by looking at this average phase factor. So when this is close to 0, then you're doing really badly because your phase fluctuations are canceling strongly. And 1 would, of course, be the ideal situation where your phases are totally coherent. And so at small imaginary time, everything is good, but one can follow these blue curves and see an exponential fall off in the average phase with imaginary time. But certain choices of the ramp really give an exponentially much better asymptotic scaling of this average phase and correspondingly of the error estimates, as we saw directly in the results. So it really is quite a significant improvement in some of these response functions. What is, however, a little weird, just to point out as a sort of final point, a weird feature of this plot, we tried these runs, these deformations, for various choices of total GFMC time. So each of these points tells me what the imaginary time separation was of the two currents in the Euclidean response. But the length of each trace is just the extent of how many time steps we ran the GFMC for. And so you would think that the ramp results at different choices of total GFMC time should be totally consistent, much like the original results are. There's actually two traces in blue stacked on top here. And this is quite sensible because in GFMC, we just evolve step by step recursively. So it would be surprising for the points later in imaginary time to have any effect on the observable that's contained to some earlier point in Euclidean time. But what seems to be the case is if the total extent of the GFMC is longer, the results in the deformed case are much worse. And one can check this by considering the kind of overall magnitude of the optimal ramp. We find this to be around 0.64 inverse MEV in some parameterization of that magnitude, which is independent of the total time, whereas the analytic argument, if you check it carefully, suggests that it should scale linearly with the total Euclidean time extent. And so our kind of working theory here is that even though there might be some really useful deformation that could improve your observable for shorter imaginary time evolution, that deformation, in order to avoid picking up a bunch of noise in the path integral, has to somehow continuously be extended to the rest of the time steps. And that can add counteracting noise that's somehow unhelpful. So I don't think this chapter of this story is quite closed. We'd like to look into this a bit more, but at the very least, there is kind of a working approach to getting decent results out of Euclidean responses. Namely, you can just work at a total GFMC time that's roughly of order the total time that you actually want to study your response function for, which is quite a natural choice in any case. Okay, so those are the kind of two proof of principle results that we have pulled out of this approach. Of course, this is really just for the deuteron, and it's very much a simple calculation. We're not using realistic potentials. So just to summarize where we're at after this work, I mean, we've seemingly worked out the details of how to deal with the analytic continuation of the potentials and the wave functions. Although Scott's question is an interesting one, I think it still remains to be investigated a bit more whether different choices have a strong effect here. But these polynomial Chebyshev approximations were a very natural choice here. And so we haven't yet explored numerically what the effect of that choice is going to be. But then this sets us up to do deformations that are exact, guaranteed by Cauchy's theorem. And by applying numerical variance optimization, one can actually see some quite promising results in the Euclidean density response functions, even though we only saw some modest improvement in the binding energy estimates. So this sets us up in principle to apply the work to larger nuclei directly. But if we do so, presumably this would be more, ideally we'd be more interested in the pheno application. So it would be necessary to work with some more sophisticated or modern parameterizations of the nuclear Hamiltonians. maybe ones that take into account N interactions. But all the machinery in principle goes through. So it's just a question of, in practice, how much time it would take to train and optimize some of these contours and see what the final effects are. And as a final kind of open point, GFMC has this structure where you need to deal with these exponentially large vectors of the spin isospin wave functions. But this limits significantly the total size of the nuclei you can access. So maybe more recent approach, more suitable approach for large nuclei would be auxiliary field diffusion Monte Carlo, or AFDMC, where this spin isospin component is also treated stochastically. And that typically introduces more of a sign problem. But since our aim is to solve the sign problem anyway, it would be interesting to ask if that could also be solved by something along these lines. So with that, thanks for your time. And I'm happy to have some discussion now or some questions as you guys like.
All right. Thank you, Tej. And if anyone has questions, speak up now. If I can check, those are clapping emojis. Okay. If I can check if I understood something on the previous slide.
Yep.
So yeah, this demonstration that the sign problem can be improved more if you have a shorter time extent. So maybe this is what you said. I think of this as, I'm inclined to think of this as you have a certain amount of room to deform your contour before you've gone so far into complex space that everything inevitably becomes very noisy. And so if you're going to have a time-dependent contour where you're deforming further and further, then the longer you want to run the time, the less deformation you can do per time step, and therefore the less improvement you can get typically. Is that basically what's going on here?
We think so, yes. The strangeness of it perhaps is that it's not obvious that, let's say I'm interested in this point here of my current or my Euclidean density response at a Euclidean separation of 0.01 inverse MeV. It's not obvious why that means you need to deform the points out here so much that they prevent you from deforming this point to as much as it could be, as you see from the shorter runs. But somehow I think it's because of continuity and trying to reduce the noise overall in the path integral. It is the case that if I was, and we can see this in the kind of ramp structure, if I was to extend the total time extent, and this is the optimal ramp given this extension of time, then clearly you would have to deform much more the points at later times. And so that presumably would be adding some kind of noise, even if you're not even interested in measuring observables there.
Your loss function, I don't remember the exact loss function, but I saw two terms. One was with regards to your observable, but the other was supposed to be the overall sign problem, right?
Yes.
The first one there. So that other one gives a penalty that cares about what's happening at late times, right?
That's right. Yeah. Okay. And even the lower one in principle cares about what's happening at late times because the full reweighting factors appear in this guy.
Ah. Okay.
So even if this observable somehow only acts on the first, let's say, m coordinates out of n, it doesn't really care. I mean, the full kind of fluctuations of those coordinates at large time are also being captured in this loss function, which is the right thing to do because they're also being captured in your estimates of the observable.
Gotcha. Thanks.
So like you're doing the contour deformation is interesting to the whole like path integral. So you have this time slice, but also you have coordinate space. And you're doing the deformation is whole like field space in the end.
Yes.
And your sort of density function is sort of basically you have like weights on each time slice, which comes from the potential term, but also you have this Gaussian like a propagator that's connecting those two time slices. Mm-hmm. And you still have this, your deformation is still like on each time slice. So your time deformation doesn't one time slice doesn't depend on the other time slices.
Yeah, in this parameterization, the simple ones that we use, there's no coordinate dependence at all in the deformation parameters.
Yeah,
So,
and then yeah,
yes.
I thought if that's the sort of if there is a good reason to do it because of the method, the Green's function Monte Carlo, I think that's really cool because we don't have to have, you know, the whole like quantum information, the whole like field space, including the time step. But is it just your choice, or like can I in principle think about doing the quantum information, the whole like entire field space, including time space? Does it improve like your method, do you think, or?
You definitely can consider doing a more general deformation over all of the time slices at once. The only problem is the usual one of your Jacobian potentially being hard to calculate, and maybe if you have a complicated parametrization, it might be hard to optimize as well. But that's a practical problem. So theoretically, yeah, you're totally fine. And especially if your parametrization that's more general contains the simpler one, then in principle, you should do strictly better than whatever we've done here. But it's just a question of how much you gain by introducing such complexity.
Okay, I see. Okay. Thank you. Yeah, I thought that, you know, because there's a simple Gaussian distribution that connects to each in the two time slices. If you did some sort of contour deformation for each time slice, then you sort of introduce some sort of fluctuation on now on this Gaussian part. Is it true?
You definitely get some kind of phase fluctuations from the Gaussians. That is for sure true. What I think of the Gaussians as doing is just trying to drive your deformations to be some kind of smooth function of tau, because they always contain some kind of r at the next time slice minus r at the current time slice. And so if the amount that you deform those two coordinates is quite similar, even if the individual deformations are very large, then the total kind of push for r at n+1 minus r at n squared into the complex direction is not so big.
Oh, okay.
So I think those Gaussians really encourage some kind of smoothness on the deformation as a function of tau, which might be going back to this weird behavior that for larger total taus, we get less performance even for the same observable at a fixed amount of tau, because by this continuity condition, you're kind of forced to continue deforming even past the end of the tau that you cared about, just to make sure that your path integral as a whole is not too noisy from these Gaussians.
Okay. I feel good. Thank you.